Hi everyone, my name is Amod. I am a PhD student at Northeastern University, Boston. Today, I'm going to present our work integrating data lake tables. This is a joint work done at Data Lab in Northeastern University with professors Royce Raga, Wolfgang Katterberg, and Rennie Miller. I'll begin with the motivation behind our work. Data lake platforms serve as repositories housing millions of tables covering a wide range of subjects. Furthermore, the data scientists rely heavily on diverse datasets to facilitate decision-making processes, conduct statistical analysis, train machine learning models, and so on. So, the data scientists can discover the relevant datasets within data lakes and use them for their task. There has been significant progress in searching for relevant datasets within data lakes. The data scientists can use keyword-based methods as well as table search paradigm to find tables for their analysis. For example, if they are looking for information about football stadiums, they can use football stadiums as a keyword to find tables related to football. Similarly, they can also use an existing table containing information such as football stadium, their location, and the home team of as the query table, and find for union-able tables, which can add more rows to the query table for vertical expansion, or joinable tables, which can add more columns to the query table for horizontal expansion. After data scientist collects the tables using different discovery methods, the next natural step is to integrate the collected tables. The integration of tables can make analysis richer as it provides a unified view of data and allows data scientists to run the queries that go beyond a single table. So in this work, we present Elite as a solution to integrate the set of discovered tables. Let's consider that our data scientist is helping a new football team having a new stadium to find their new coach. Accordingly, the football team wants to have a coach who has an experience of handling the teams playing in front of large crowds in new stadiums. Consider that the data scientists already collected these 5 tables about football using different search techniques. Here, table T1 and T5 have information on football stadium, location, and team. Table T2 has information on when the stadiums were opened. Table T3 has an information about coaches of different football teams, and table T4 shows the capacity of different stadiums. The plus minus symbols in this table represent a null value that is present in the collected table. Also, PID is not a real column, and we use it only to refer the tuples. So on what follows, to fulfill the team's requirement, the data scientist may want to run the query such as find the coaches who coach teams having stadiums established after 2000 that accommodate at least 50,000 spectators. Based on the collected tables, the answer to this question is Dan Campbell, who coaches Detroit Lions that uses Ford Field Stadium as their home stadium, established in 2002, and having a capacity of hosting 65,000 spectators. And to answer this question, we need collective information from multiple tables, at least from tables T2, T3, and T4. This shows the benefit of integrating multiple tables in order to answer the queries which go beyond a single table. Now that we saw an importance of integrating the tables, let's see the possible issues with table integration. Integrating the collected tables mainly faces 2 issues. First, it is generally unclear which columns from the input tables to align together in the integrated table. In relational tables, such information is generally provided by the column headers in the tables. However, in case of data lake tables, we cannot rely on column headers because they can be inconsistent between the tables, as the table may be collected from different sources using different source techniques. For example, in both tables T2 and T3, we can have the same column headers for non-aligning columns, such as name as column headers for stadium column in T1 and team column in T3. And it is not a good idea to align them just because they have the same column names as their semantics is different. We can face the similar problem in opposite direction as well. That is, different column names but same semantics, such as location column in table T2 and state column in table T3 for aligning columns. An option would be to apply schema matching between the tables, but in our scenario, applying schema matching over a pair of tables is not enough either, because we want to integrate a set of tables rather than just a pair. Therefore, in this work, we develop a hierarchical clustering-based approach that determines the matching columns in a holistic way. Furthermore, even if we resolve the column headers and figure out which columns to align together, the second issue is that we still need an integration operator to integrate the tables together. and the basic operators may not be effective for our problem. For instance, the basic union operator needs all the tables to have exactly the same columns. An alternative would be to project out the matching columns and integrate the remaining ones. But doing so, we again miss information. For example, in this case, we will be left only with location column on applying union operator after projection. Similarly, the natural inner join operator also misses an integrating tuple, even if the joining tuple is absent in one table among all we integrate. For example, if we inner join these 5 tables, then we will get no tuples in the integration result, since none of the tuples have joining partner in all the tables. And this is a very common case in integration of the source results. Next option would be to use the combination of join and union operator. However, this is also challenging because the order of using the operators will impact the final result. Alternative could be a natural outer join operator that solves the problem seen in inner join operator and retains a tuple even if it does not have a joining partner in all the tables. But again, the outer join operator is not associative. And when integrating more than 2 tables, the order of integrating the tables could impact the result. For example, we get different integration result if we integrate tables in the order T1 to T5 versus T5 to T1. Therefore, in this work, to integrate the discovered tables, we propose to use a scalable implementation of full disjunction operator that was developed in the 90s and used to integrate the relational tables. Now I will briefly explain the full disjunction operator. Full disjunction is an associative extension of outer join operator that integrates the input tuples in a holistic way so that the order of integration does not matter. Full disjunction generates output tuples that are maximally integrated. And by maximally integrated, we mean that there are no tuples that are contained in another tuple in the integration result. Also, integrating the tuples maximally gives us the complete information available in the input tables. For example, tuples T6, T9, and Tu11 are integrated maximally, and that gives us an information about Dan Campbell that our data scientist was looking for. And note that whenever we do not have complete information, the integration yields null values. For example, since the capacity of Lambu field is not available in the input tables, the capacity columns is null for this tuple. So here is our full solution for the table integration problem. We call our solution as Elite, which indicates its 2 phases of integrating the tables. First, align, and second, integrate. In align phase, we identify what are the columns that should be integrated together or that should be aligned together in the integrated table. We use a clustering approach to determine the set of aligning columns. Then for each set of aligning columns, we assign an integration ID. Next, in the integration phase, we use the integration IDs assigned in the first phase as input, and then we integrate them using our novel full disjunction algorithm to output an integrated table. Now I will briefly explain the align phase of our algorithm. The input to the align phase is a set of tables to be integrated, and this phase outputs different sets of columns annotated with their integration IDs. To do such annotation, we first embed each input columns using their values. Then we apply hierarchical clustering over the embeddings, which gives us a dendrogram showing all possible clusters. After that, an important decision is selecting the number of clusters, which will be the number of columns in the integrated table. For this, we determine the clustering quality score for each number of clusters as shown in the graph. We select the number of clusters that maximizes the clustering quality score. For example, the number of clusters will be 6 as it gives the best clustering quality score in this example. We measure clustering quality score using Sill-Outage coefficient, which gives better result than other measures based on our experiments. After we determine the clustering, after we determine the columns together, we assign them with a dummy column header, which we call integration ID. These integration IDs serve as column headers during the integration phase. Once the align phase gives us the tables with columns annotated with their dummy column header, we apply our novel full disjunction algorithm over the dummy column headers to get an integrated table as output in the second phase, that is in integrate phase. Full disjunction has been used to integrate the relational tables in the past. The prior work computes full disjunction using different concepts such as computing outer join for all possible ordering of table schemas and removing the subsummable tuples, or reducing FT computation as weak matching problem. Similarly, more recent works compute FT by partitioning table schemas into bi-connected components or by applying outer join over all spanning trees that can be generated from the input schemas. In this work, we propose a new way of computing full disjunction by adopting complementation operator so that it practically scales the FT computation for table schemas, forming complex cycles and having no primary key to foreign key relations like in the prior work. Now I briefly explain the building blocks of our full disjunction algorithm. First, we define two different kinds of nulls: missing nulls, which are the null values in the input tables, and produced nulls, which are the nulls that are produced during the integration process due to incomplete information. Note that we handle these two nulls differently during the integration process. Next, I will explain the involved operators. We develop our algorithm using other less known operators such as outer union, complementation, and subsumption. Outer union operator is an extension of the union operator that pads the unknown columns on each table with null values. For example, we pad opened column on tuple from table T1 with produced nulls as this column is not available in table T1. Second, we use complementation operator to develop our full disjunction algorithm. Complementation algorithm combines two tuples having the same non-null values if they also have at least one more non-null value where other tuple is null. Complementation helps us to combine the joining tuples. For example, when we apply complementation over the tuples in outer union table, the first and fourth tuple having Ohio as location are combined to give the first tuple in the resulting table. Next, we use subsumption operator. A tuple T1 subsumes tuple T2 if tuple T1 contains all the information in tuple T2 and tuple T2 has more number of null values. Subsumption helps us to get rid of the tuples containing partial information. So for example, in the table after applying complementation, the second tuple about Sophie Stadium subsumes the last tuple about Sophie Stadium having the same information but more null values. So the last tuple is removed after applying subsumption as shown in this table. Build our full disjunction operator, we use a fixed sequence of outer union, complementation, and subsumption operator. The key idea is that we produce maximally integrated tuples using complementation operator and remove subsumable tuples using subsumption operator if they are produced. Note that we handle missing nulls and produced nulls differently while applying complementation operator to avoid undesirable complementation. For example, based on full disjunction semantics, we do not want to combine the first tuple from table T1 with the first tuple from table T5 just because they are both from Ohio, since their other aligning columns, stadiums and teams do not have the same value. We can see that the team is null in table T1 and stadium is null in table T5. Our idea of only complementing over the produced nulls helps us to get rid of this issue of undesirable complementation. And please visit our paper for further details. I will now present some experimental results from our paper. To run the experiments, we used 4 different benchmarks: Align, Real, Join, and IMDb dataset. Each benchmark contains different set of tables called integration set, which are integrated together to obtain an integrated table. For example, there are 65 integration sets in Align benchmark, which means we run 65 different integration with the tables in this benchmark. For Align phase, we compare Elite against the schema matching techniques available in Valentine package. We use BORT, FastText, and TURL based pretend embeddings to create 3 different Elite variations. Based on our experiments, Elite based on TURL embeddings, which is the model pretend using tables, outperforms other methods in terms of F1 score by over 4% in real benchmark. Furthermore, we also compare the runtime of Elite's full disjunction algorithm against BICOM analogy and para-FT and observe that in average, Elite is faster by an order of magnitude than the second best baseline, that is BICOM analogy, in real and joint benchmarks. For more experiments regarding the efficiency, please visit our paper. Next, we also evaluate if we need full disjunction in practice instead of using outer join operator. For that, we measure tuple difference ratio between full disjunction and outer join. We integrated the input tables using both full disjunction and outer join separately, and then reported how many full disjunction tuples, that is maximally integrated tuples, can outer join produce. We saw that outer join produces all FT tuples only once, and it produces more than 50% of maximally integrated tuples only for 3 times, which shows the benefit of using full disjunction. We also run entity resolution as a downstreaming task after integration, and we saw that applying entity resolution over full disjunction integrated tuples give better result. That is, the F1 score is higher by 45% than F1 score of applying entity resolution over outer join tables. This further shows that full disjunction is better choice to integrate the discovered tables. So in summary, today we presented the problem of integrating the data lake tables after they are discovered using different source techniques and present Elite as a solution. We saw that Elite outperforms existing system in align phase in terms of F1 score, and it is practically effective and efficient than the baselines in integrating real tables. Our benchmarks and codes are publicly available in our GitHub repository. Thank you so much for listening, and please do not hesitate to email me for any questions.